Alright, so in this video we're going to solve problem 6.17. We're given a truss with an unknown applied load P, and that truss is supported at two locations. It's supported at point E and point C, and both of these are pin joints. Alright, we're also given the relative dimensions of each of the members of the truss, so we can determine the angles between all the of all the truss joints. All right. So what we're asked in this problem is we're asked to determine what is the greatest value of P that may be applied to the truss, so none of the members are subjected to forces that either exceed 2.5 kilonewtons in tension or 2 kilonewtons in compression. All right. So 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 to solve this problem, uh, since we need to know the force within all of the members, so since we need to know the force in all the members, this is a hint that we should probably use the method of joints. All right. So for the method of joints, all right, the key thing that we need to know is we need to identify a joint with at least one known force and at most two unknown forces. All right. So if we look at this diagram here, uh, all right, we can see that at point A, we have a known force P, all right, and we have two unknown forces. We have the force within member AD, and we have the force within member AB. Okay, so what we're going to do is we're going to draw the free body diagram at point A. All right, so at point A, we will have our applied force P. We will have our force that goes from point A to point B, and we have our force that goes from point A to point D. All right. Now, force AD goes along a 2 meter. It goes has a dimension of 2 meters in the x direction, and then 1.5 meters rise in the y direction. So the length of remember AD would be equal to 2.5 meters. And then we could do the same process for AB. It just goes down instead of going up. So it's also 2.5 meters long. So what we can now do is we can use the uh, equilibrium equations to solve for these two unknown forces, FAD and FAB, all in terms of P. All right, so the goal of the problem here, or is we want to determine the force within each member in terms of P, or in terms of the applied force. All right, so the first thing we can do is we can say we're going to sum all of our forces in the x direction, and we're going to set that equal to 0. So if we do that, what we'll end up getting is we'll get 2 meters over 2.5 meters times FAD plus 2 meters over 2.5 meters times FAB. All right. The reason we're using the ratio of the sides of the triangle to determine what would be the horizontal component of FAD and FAB. All right. So if we evaluate this, what we end up getting is that FAB will be equal to minus FAD. Right. So now we can use our second equilibrium equation, which is we're going to sum all the forces in the y direction and set them equal to 0. So we get negative P plus 1.5 meters over 2.5 meters, all right, times FAD, all right, minus 1.5 meters over 2.5 meters times FAB, all right. We can substitute for FAB. We're going to substitute in negative FAD from over here, all right. And if we do that, we will get what we'll end up getting here is we'll get P will be equal to 1.5 meters over 2.5 meters FAD plus 1.5 meters over 2.5 meters FAD. What we'll end up getting is that we'll get that FAD will be equal to 5/6 times P. All right, and from this equation here, from the sum of the forces in the x direction, we know that FAB will be equal to minus 5/6 times the applied force P. So, all right, so that's our first joint. All right, so then the next step would be to identify another joint that has one known force and two unknown forces. So if we look at joint B, okay, all right, we're gonna have we're going to have one known force, which is the force within AB, and we have two unknown forces, the forces within BD and the force within BC. All right, so we can draw our free body diagram at point B. All right, and if we do that, we'll end up getting so we'll get force AB. All right, force AB is going to be in compression because, or going into the joint because it's negative. We found out it was negative earlier, so we're going to say this will be, let's see, it'll be 1.5 meters in the y direction, 2.2 meters in the x direction, and its length is 2.5 meters, and we know that the magnitude is going to be equal to 5/6 P. All right. Then we have two additional forces. We have the force within BD, all right, and we'll draw that in tension, all right, and then we'll have the force within BC, all right, and we'll draw that in tension as well. So force BC, just like force AB, will have a horizontal distance of 2 meters, a vertical distance of 1.5 meters, and a length of 2.5 meters. All right, so we're just going to use the equilibrium equations again to solve this problem. So we're going to say we're going to sum. The first thing we're going to do is we're going to sum all the forces in the x direction and set that equal to 0. All right, so the x direction, we're going to have the horizontal component of FAB, so that's going to be equal to 2 meters over 2.5 meters times the magnitude of FAB. So FAB, the magnitude of FAB is equal to 5/6 P. All right, and then we're going to have, also we're going to have 2 meters over 2.5 meters times FBC for the horizontal or the x component of force BC. All right, FBD has no x component, so we don't need to include it in this equation. All right, what we'll end up getting here is we'll get FBC is going to be equal to negative 2.5 meters over 2 meters times 2 meters over 2.5 meters times 5/6 p. Alright, so all of these terms will cancel out and we'll end up just getting minus 5/6 p. Alright. Alright. So then for FBD, alright, so to solve for FBD, what we then need to do is we need to sum all the forces in the y direction and set that equal to 0. So if we do that, what we end up getting is we'll get FBD, which is going along the positive y direction, and then we'll get minus 1.5 meters over 2.5 meters times 5/6 p. All right, that's for this is for force AB, the y component of force AB. All right, minus the y plus, I should say plus the y component of FBC, which is going to be equal to 1.5 meters times 2.5 meters times the magnitude of FBC, which is going to be equal to negative 5/6 p. All right. So if we rearrange this equation, what we end up getting is that FBD is going to be equal to 5/6 p times 1.5 meters over 2.5 meters plus 1.5 meters over 2.5 meters. So those are both 3/5. So we would end up getting 6/5 times 5/6. So we'd end up getting FBD would be equal to P. Alright, and since it's positive, FBD would be in tension. Alright. So, so now we would look back at our free body diagram again, and we would try to identify our unknown forces. Alright, we're trying to again identify a joint that has at most one known force and at least one known force and at most two unknown forces. So now, since we know the forces within AD, within BD as well, we know that at point D we have two unknown forces, DE and DC. So we can try to solve for those two unknown forces within those two. All right. So we're going to draw a free body diagram at point D to solve for those two unknowns. All right, so at point D, we're going to have the force within dA, all right, which we solved earlier, and we got 5/6 p. We also have the force within dB, the member from point D to point B, all right, that's equal to P. We just solved for that in the last problem. And then we have the force within DC, all right, and that goes along a 2 meters along the x direction and 1.5 meters along the y direction, so its length will be 2.5 meters. And then we have force DE, all right, which has a 2 meter length in the x direction and a 1.5 meter length in the y direction, and it also has a length of 2.5 meters. All right, so we can use the equilibrium equations again to solve for our two unknowns. So if we sum the forces in the x direction first, so let's do that. All right, we'll end up getting we have to include the x component of FDA. So FDA's x components would be negative 2 meters over 2.5 meters times 5/6 p. All right, so that's FDA. And then we'll have the the x component of FDE, which would be equal to 2 meters over 2.5 meters times FDE. And then we'd also have a ratio of 2 meters over 2.5 meters for the x component in FDC. All right. So if we rearrange all of this, what we end up getting is you could set FDC equal to uh, so FDC, we can move everything to the other side, and we end up getting 5/6 p um, uh, minus FDE. All right, so we can use that relationship in when we find the sum of all the forces in the y direction and set that equal to 0. If we do that, what we'll end up getting is uh, we'll get negative p due to force dB. We would get uh, minus 1.5 meters over 2.5 meters times 5/6 p due to force dA. And then for the y components of FDE and FDC, we would get for uh, FDE, we would get plus 1.5 meters over 2.5 meters times FDE. And then for the y component of FDC, we get minus 1.5 meters over 2.5 meters times FDC. All right, so FDC, we're going to plug in this relationship here where we had 5/6 p minus FDE. All right, and we should be able to then solve for FDE. All right, so if we evaluate all of this, what we should end up getting is we'd get, we're going to move all the known terms to the left-hand side of the equation. So we would get p plus 2 times 5 plus 0.5 p. Um, uh, then we get, let's see here, plus, if we do this again, that would be plus 0.5 p. All right, so those are all of our known terms here. All right, so our unknown terms are going to be 1.5 meters over 2.5 meters times FDE. All right, plus 1.5 meters over 2.5 meters FDE. All right, so what we end up getting is we'll get 2p is going to be equal to 3/5 plus 3/5, so that should be 6/5 FDE. So if we rearrange that, we'll end up getting FDE will be equal to 10 over 6 times p, all right, which is the same thing as 5/3 p. All right, from the sum of the forces in the x direction, we can substitute in that value of 5/3 p, so we would get FDC would be equal to 5/6 p minus FDE, which is equal to 5/3 P. So if we do that, 5/3 P is the same thing as 10/6. So we'd end up getting minus 5/6 P for FDC. Right. So, so now if we go back to our original problem, or the first trust now we actually have all of the members of the trust we've solved for. All right. We could, now that we know all the forces within all the truss members, we could solve for the reactions at the pin joints. So if you wanted to do that, you could. You would just have to draw the free body diagram of the pin joints, and you could solve those. So if you did that, you would have ended up with, you would have gotten for the reactions at C, you would have gotten Cx would have been equal to 4/3 P. All right, so it would have been going along the negative x-axis. Cy would have been equal to 0, and then we would have gotten for at point E, you would have gotten for E of x, you would have gotten 4/3 P, and then for E of y, you would have gotten just P. All right. All right. So anyhow, if we go back to the problem statement and ask to determine what would be the maximum force that you could apply to prevent the forces from exceeding 0. So what we need to do now is we need to look at the members of our truss that are in compression and the members that are in tension. So if you do that, we have the members in compression. All right, so our members in compression are FAB, FBC, and FDC. All right, all of these actually had the same value for their for the force being applied to them. So they were all equal to minus 5/6 P. All right. Then if we look at the members in tension, all right, we can determine that we have member AD was equal to 5/6 P, member FED was equal to 5/3 P, and then member FBD was equal to P. All right. So our maximum force in any member in compression was equal to minus 5/6 P. All right. All right. Our max force in tension was equal to 5/3 P. All right. So in the problem statement, we were told that the maximum allowable compression force was equal to 2 kilonewtons. All right. So if we plug that in and we solve for P, the maximum allowable force P would be equal to 6/5 times 2 kilonewtons. All right, so that would be equal to 12/5, which is equal to 2.4. Yeah, 2.4 kilonewtons. All right. So then you had to repeat the same process using the maximum allowable tension force, which was given to us as being equal to 2.5 kilonewtons. All right, and solve for P. So the maximum force now, if we solve for P, would be equal to 1.5 kilonewtons. All right. All right. So since 1.5 kilonewtons is less than 2.4 kilonewtons, the maximum allowable force that could be applied to the truss would be equal to 1.5 kilonewtons. Okay. So So in this type of problem, you would use the lower value of P. So that concludes this example problem of how you use the method of joints in order to solve the uh, for all the forces within the truss, and then determine what would be the maximum allowable applied force based on the capacity of the members.